Unfortunately, the test won't come before midterm grades are due. And so I have to base the midterm grades on what I have. And I'm gonna wait it like tests are 70% of the class, homework's 30%. So if you did poorly on the test, your midterm grade may not look that good.
Are we gonna make our questions again?
Yeah, we can do that. Would you guys like to
Can we do
that?
it a little bit earlier, like instead of showing it the very last day?
All right, how about next
Maybe.
Wednesday?
Okay.
I can do that.
Okay?
You're well away.
That'll give you a next
But
Wednesday.
yeah.
Next one.
Yeah, just pick your group again.
Okay.
4 or 5, everyone should be in it.
Okay.
Yeah, we do that. This one is better do that. You should.
Okay. So, we're gonna start covering a new topic called momentum. And unfortunately, I forgot to bring demonstrations down here. Oh well. So we know that the sum of forces on an object F is equal to mass times acceleration, right?
Yeah.
We also know that acceleration of an object is equal to its final velocity minus its initial velocity divided by the change in time it took to go from initial to final. Is that familiar with everyone? Let's take this, plug it back into here. So we can say F is m times v final minus the initial velocity over the change in the time to go between those. And if I distributed this m, I'd get m v final minus m v initial over the change in time it took to go from one to the other. Well, this quantity of mass times a velocity seems to arise naturally writing F equals ma like this. And we'll see that this way of writing F equals ma turns out to give us some interesting things. This quantity mv is actually called the momentum of the object. So momentum, which is symbolized with something that makes a good sense, P, with a vector, is mass times velocity of an object. Okay? And this means that the force on the object can be this is the total force on the object, can be written as ma, which can be rewritten as the final momentum minus the initial momentum. See, this would be the final momentum of the object. This would be the initial momentum of the object, divided by the time it took to go from one state to the other. Okay? Or I could write that the final momentum of the object minus the initial momentum of the object is the total force on the object times the time that that force acted for. Okay? Nothing new here. This is just a way of rewriting F equals ma and introducing a new quantity, which we'll see in a little bit will aid us in dealing with things like collisions. But let's take a look at this real quick. Let's say I have a massive object, m equals, say, 10 kilograms, okay? And let's say I just let it drop this object. How fast is it going? seconds later. Of course, you can do this with knowing the acceleration, and just multiply the acceleration times the time. Let's do it with this momentum thing here, okay? So use momentum. And so what I'm going to do is I'm going to just apply this formula here. So this probably isn't the best way to do this problem, but it's a way. So the initial momentum is equal to m times the initial speed velocity. And what was that if I just dropped it from rest?
0.
0. Okay, what's the final momentum? Be m times the final velocity. That's what we want to figure out, right? So that means that P final will be this change in momentum. It will be P final, right? So that'll just be the total force times the time that the force was applied for. What's the force on an object that's falling?
mg.
mg, yep, downwards. So we would get, this is final. So we would get that m v final is equal to the total force. If I introduce my y and x coordinate system like that, what's the total force in vector, written as vector? Negative m g y hat, right?
Yeah.
Times the time that it took, 2 seconds. Okay. That makes sense. What I'm doing, just divide through by the m, and I would get that v final is equal to minus g times 2 seconds y hat. Okay. Which would be negative 19.6 meters per second y hat. Straightforward, right? You might ask, why would I do this? Why would I introduce something named momentum just so you can do this, something like this? And the answer is, it really isn't just so you can do something like this. Momentum really, really is important when you have two objects interacting with each other and exerting forces on each other. That's when the momentum becomes very useful. So let's take a look at what happens if we have two objects that are exerting forces on each other. Okay? So let's say I have a mass 1 and a mass 2. And somehow or other, with some sort of force, it could be a rope between these, it could be them hitting each other, there could be magnets. Somehow they're exerting forces on each other. And let's just say, I'll just draw this line. We'll write this as the force on object 1 by object 2. And what does Newton's third law say about the force on object 2 by object 1?
Equal.
Yes. So they're in opposite directions, and they have the same magnitude. This would be the force on object 2 by object 1. You remember that? Okay. Well, let's go ahead and look at, let's say that these are the only forces on these objects. I have two objects, the only forces on them are when they're acting on each other. Let's see what happens when we look at this momentum thing here. So let's look at object 1. We could say that F12, F on object 1, force on object 1 by object 2, times the time that it acts for. What would that be equal to? In terms of momentum, it would be the momentum on object 1, the final momentum, minus the initial momentum of object 1. right? Does that make sense? The force on object 2 by object 1 times the time that it's acting for would be the momentum on object 2 the final momentum on object 2 minus the initial momentum of object 2. Right? Make sense? These two things are equal and opposite. So that means this is the negative of this by Newton's third law. So F(1,2) is equal to negative F(2,1) by Newton's third law. Let's go ahead and plug this in. The times that these forces are acting for will be the same, right? Because whenever there's a force exerted on 1 by 2, there's a force exerted on 2 by 1. So these times will be the same. Let's see what happens when I just write this out. I would get, so this means force on 1 by 2 times the time that it acts on, plus force on 2 by 1 times the time that that force acts. What's this going to be using this?
It should be 0.
0, right?
Mhm.
That's equal to 0. Now, I'm going to take this and plug it in for here. I'm going to take this change in momentum and plug it in for here. And what I see is I see the final momentum minus the initial momentum of object 1 plus the final momentum minus the initial momentum of object 2 is equal to 0.
Wait, why didn't you leave out the time?
Yes, I could divide through this by a delta t, right? So that's the same. And then I just plug that in here. Now what we end up with, and then we're almost done. But this is a derivation. I'm going to group together those things that are initial, and I'm going to group together the things that are final. And I see that if I do that, P1 final plus P2 final minus P1 initial minus P2 initial is equal to 0. I can bring all these initial things over, and I would get that P1 final plus P2 final is equal to P1 initial plus P2 initial. All right, so here's what we've shown. And this is just what I wanted to show today, and then we'll do some examples. We just showed that the total momentum, the sum of the momentums of each of the objects before they interact with each other, that'd be this, right? Before they exert forces on each other, will be the same as the sum of momentums after they act on each other. And we didn't even need to know the details of the forces they exerted on each other. We just need to know that if they're exerting forces on each other, the sum of momentums before will be the sums of momentums after. That was a consequence of Newton's third law we saw. Or another way to put it is that momentum is constant before and after they interact with each other, the sum of momentum, or momentum's conserved, we call that. So let's go ahead and do an example. So this will be just going to box this. That's going to be our key useful thing. This comes up mostly in this class in something called collisions. These are where two objects hit each other, while they're hitting each other, they're only exerting forces on each other. And then the net force, all the other forces like gravity and normal force, they'll kind of cancel out. So they don't change momentum. So while they're hitting each other, you know, that's they're interacting with each other, we can apply this conservation of momentum. So let's take and say I have a mass 1. It's initially, I'm going to write initially, that means before any collision. Mass 1 is moving with a speed of, let's say that's 10 kilograms. And it's moving with a speed of 10 meters per second in that direction. And let's say it hits a mass 2 that is initially at rest. Let's say that after the collision, and exactly what happens during the collision depends on the nature of the collision. We'll talk about that later. Let's say after the collision, mass 1, oh, this is also 10 kilograms, by the way. M1 is moving with a speed of 2 meters per second. M2, let's say that this, we don't know. Okay? We don't know what speed it's moving at. Now the question is, can you use momentum to figure out this V? So find V for M2. Question mark. I'll go ahead and let you guys give that a try. You can work with the people next to you. Just see if you can get that real quick, and then I'll go do it. Take about 2 minutes. Initially, yeah. Yeah, that's it.
Yeah, I just wasn't sure if it was good for all that.
No. Once you have that final equation, you're done. That's just derivation. So you see where that comes from.
Yeah.
Okay, you ready? What do you guys get?
8 meters per second.
8 meters per second? All right, that's right. Let's go see if we can, let's go apply this conservation of momentum and see why. So we'll do this in gory detail for this first one. Let's say that we introduce our X and Y coordinate system. We're dealing with vectors here. And I'm just going to use this equation here, okay? So my initial momentum is M1. Let's do P initial, P1 initial plus P2 initial is equal to P1 final plus P2 final. By definition of momentum, it's just mass times velocity. So I would get that this would be M1 V initial plus M2 V initial for 2, initial for 1. What was this? 0, because it wasn't initially moving, is equal to P1 final, which would be M1 V1 final, plus P2 final,
2 meters per second.
plus M2 V vector, which was what we were looking for. All right, plugging in numbers, this would be 10 kilograms times 10 meters per second x-at for this first one is equal to 10 kilograms times 2 meters per second x-at plus 10 kilograms times v. Notice the 10 kilograms cancels. I can divide the whole equation by 10 kilograms. And so I see that 10 meters per second x-at is equal to 2 meters per second x-at plus v. Subtract 2 meters per second from both sides. And 8 meters per second x-at is equal to v. That was in very detail. Now, let's go do another example. I'll give you guys a chance to do this one, okay? Oops. So, now we have somehow a slightly different collision. Let's say that we have a 20 kilogram mass traveling at 10 meters per second in the x direction. And let's say you have a 10 kilogram mass traveling at 10 meters per second in this direction. So it's sort of a head-on collision. Let's say that the collision was such that afterwards this 20 kilogram mass was traveling at 5 meters per second. What's that 10 kilogram mass doing? What is I won't even put the direction on that one. So see if you can figure out what this is. All right, this time take another about 3 minutes, okay? Did everyone get these homework? Okay.
There's some that make sure they go past that.
got it?
Um,
All right, what's it doing? It's not moving?
That's what I got.
Is that what everyone got? All right, well, let's go see what happens. So,
Is it 20 meters per second?
we'll go see, we'll go see.
Okay.
So you have 20 meters per second and not moving. So let's go ahead and do this. Again, we'll do this one more time in gory detail. One thing that's useful, if I only have movement along one direction, see how these are vectors? I could write this as actually three sets of, maybe in the, three sets of equations. I could write this as P1, P initial 1x plus P initial 1, or P2 initial x is P1 final x plus P2 final x. I could write it like this, so the x part of the momentum is conserved. So the total sum of the x part of the momentum before and after, and then the x part of the momentum would be whatever the mass is times the velocity in the x direction. Okay, so I'm gonna use this. I could also, this thing also implies that the same thing would hold for y as well. So I'm gonna write these as components right now because I have everything in one direction. So I'm gonna x directions like this. So this initial momentum, let's see if we can do this. Initially, I would have 20 kilograms times 10 meters per second in the positive x direction. And then what would this be?
10 and 10.
It's moving 10 meters per second that way, right? So
Oh,
that's,
so it's be negative.
so it'd be negative 10 meters per second in the x direction. So minus 10 kilograms times 10 meters per second is the initial momentum. Do you see where this minus sign comes from? That's just it's moving in the negative x direction. Now that has to equal the final momentum. So 20 kilograms times 5 meters per second plus 10 kilograms times v.
10.
Dx, okay? Now this is 200 minus 100 kilograms meters per second. And then, so that's 100. I have 100 kilograms meters per second is equal to, and then this is 100 kilogram meters per second plus 10 kilogram dx. That's an equal sign. Well, if I subtract 100 kilograms meters per second from both sides, I'd get 0 is equal to 10 kilograms times Vx, so Vx has to be 0. Okay? Did you follow that? I'm sorry, it gets kind of messy down here, it's hard to write low. You want to do another one? Please, slow down.
The other one does not move. That means the construction, the other one up.
Well, maybe they didn't quite impact, they just interacted with each other. So they are exerting forces on each other, and then at some later time, one's moving.
Weren't they in that both their insurance and all that? We got a Cadillac there.
I see what you're saying, that, you know, if they hit, then this one would still be moved, you know, how could they go past each other? Well, let's just say that this is far away, and then it's a little later time after they've been interacting, they never hit each other. At some later time, they're doing this. Okay.
Is there a specific unit for momentum or?
There's not a specific unit, surprisingly, it's just a MV, so it's kilograms, meters per second.
So do you just put kilograms meters per second?
Yeah. Yeah, I don't know why there's no specific unit, it's pretty useful concept. Okay, so let's do another one. Let's say we have a car collision. Okay, let's say I have a 1,000-kilogram car. This is a pretty light car, but the number's good. Going at 50, going crazy fast at 50 meters per second. Okay, so this person's a Mazda Miata going nuts, and then they hit a truck, a parked truck. But the guy has his brakes off or something. At rest. So there's no external forces. And the truck, let's say, is just 10,000 kilograms. And it's at rest. So this would be the initial. After both of these things are stuck together and are traveling with some unknown speed. Can you find the speed here?
We're assuming that there's any weight. Correct.
But yeah, they're now stuck together. You know, Mazda glommed onto it. And now they're traveling together at some unknown speed. What's that speed? Got it? What do you get?
4.5.
4.5. All right. Anyone else get anything different? All right, let's go ahead and check this out. So initially, PX in the initial, you can call this 1 and 2. PX initial for 1 plus PX2 is just going to be 1,000 kilograms times 50 meters per second, right?
Yeah.
Which would be 50,000 kilograms meters per second. Finally, PX2 final. That would just be M1 plus M2. What's the two M's? added together?
1,000.
11,000.
Yeah.
11,000 kilograms times feet. These two things have to be equal to each other, right?
Mm-hmm.
So I would get 50,000. And I hate using numbers, but I seem to be using them. Is equal to 11,000 kilograms times feet. So I just take that 50,000 and divide by 11,000.
Yeah.
Equals 50,000 divided by 11,000 kilograms meters per second over kilograms, and that's equal to 4.5, right?
Yeah.
Good.
Can you expand the second part, the P, X1, F, and then P? Can you expand that real quick? So
PX1,
the second part?
this one,
Yeah, because then that's the
and
second.
so this would be the 1,000 kilograms times V plus 10,000 kilograms times V. Because they're moving at the same velocity if they're stuck together. That make sense?
We're treating this as if there's no friction on it.
Yeah. No friction during the period of collision between these 2 points. Yep. So the guy so this truck has its brakes off. He'll get hit, he gets hit. Okay. So this is we've been looking at conservation of momentum. This is a special type of collision that we'll deal with in the future. A collision where the final two objects are stuck together and moving with the same velocity. That's called an inelastic collision. This means after the collision, the two objects are stuck together. Are stuck together and are traveling with the same velocity. Well, I mean, it's not separate. If they're stuck together, of course they're going to be traveling with the same velocity, but we'll just write this explicitly. With the same v. Okay? This is to be distinguished. There's one other type of collision we'll deal with, and that's called an elastic collision. I suddenly can't remember how to spell it. Does elastic have two L's or one? I've written that probably 10,000 times. I suddenly can't remember. Oh well. So, an elastic collision is the other special type of collision that we'll deal with. In this one, it turned not only is momentum conserved, but the actual kinetic energy of the objects is the same before and after. So kinetic energy is the same before and after the collision. These are the two special types of collisions we'll deal with. In 2 dimensions, like on the board, If I know everything if I know the initial velocities and the initial masses, in either of these collisions, I'll be able to figure out both the final velocities of the objects. The elastic collision, a little bit trickier than this one, but we can go ahead and, yeah, let's go ahead and do an example of this one. We already did one with the colliding cars where they're stuck together after the collision.
So when you say kinetic energy, is that, it doesn't mean momentum, right?
Nope, kinetic energy is 1/2 mv squared, remember?
Yeah.
So the total kinetic energy, the sum of the kinetic energy of the mass is the same before as after the collision. You can, and there's all sorts of intermediate types of collisions. All the intermediate types you can't beforehand just know what the initial velocities and masses are and then get both of those initial velocities, final velocities and masses afterwards. You have to, you can just get one of the final ones in all the intermediate types of collisions. And you can basically tell whether something's elastic if the object looks exactly the same before and after the collision. So the object doesn't get excited or moved or bent in any way or anything like that. It's probably an elastic collision. If the objects don't change during the collision, it's elastic. If they get deformed, like clay or something like that, it's probably going to be inelastic. Yes, that's right. Pool is generally elastic collisions. Okay. And so we'll learn some of the, we'll end up showing, you know, that if you hit like two pool balls, that they'll diverge at right angles, you know. You'll be able to see that. We're not taking into account spin effects. That makes everything more complicated. Yeah, English is no good for this. Yeah, friction and all that stuff. All right, let's go ahead and look at do one inelastic. Oh. All right, see you guys next week. Here's homework. If your friend didn't get one and they're not here, too bad.
Too bad. I thought you were going to say something.